of gases from the ideal being. Definition of gases from the ideal being. And we all know that almost all the gases, they show deviation from the ideal behavior. What is the cause? Because this is the T is equal to nRT. This is the ideal gas equation. And this ideal gas equation is based on kinetic theory of gases. And in kinetic theory of gases, there are two faulty assumptions. There are two faulty assumptions. What are those faulty assumptions? Number one, total volume of the gas and actual volume of the gas, they are very much different. And exactly, actual volume of the gas is negligible in comparison to total volume of the gas. Actual volume of the gas is negligible in comparison to total volume of the gas. This assumption is faulty. And number two, there are no intermolecular interactions. There are no intermolecular interactions between the gas molecules. Interactions means either attractive forces or repulsive forces. There are no such interactions in the gas molecules, and this is also faulty assumption. But these two faulty assumptions becomes valid when volume is higher. When volume of the gas or total volume of the gas, it is very, very higher, then obviously gas molecules, they will be farther apart, they will be away from each other, so there will be no intermolecular forces, and obviously when actual volume of the gas or total volume of the gas, that will be higher, then actual volume of the gas will be reduced. So this is the reason that these two faulty assumptions becomes valid when the volume is higher, and obviously when the volume is higher, then all the gases behave ideally. Why all the gases behave ideally when volume is higher? Because these two faulty assumptions becomes valid. So let us use these faulty assumptions in developing a new equation of state, which is known as Wahl's equation of state. Wahl's equation of state. Now PV is equal to nRT. That will be changed. PV is equal to nRT is the ideal gas equation, and it will be changed, and we will develop a new equation which will be Wahl's equation of state, and it will be for all the gases. It will be for real gases or non-ideal gases. So what are two faulty assumptions? Number one, that is related to actual volume is negligible as compared to total volume of the gas. It means we will make volume correction. We will make volume correction. And this is very, very important point. Suppose this is one gas molecule and this is another gas molecule. What radius and this is the radius of second molecule, what will be the volume of this sphere or molecule? 4 by 3 pi r cube. And what will be its volume? 4 by 3 pi r cube. Total volume will be 4 by 3 pi r cube plus 4 by 3 pi r cube, and it will be 8 by 3 pi r. This is the actual volume. Actual volume. This is the actual volume. But these gas molecules, they are not stationary. They are moving. So if this molecule is moving around the other, or this molecule is moving around the other, then this will be the excluded volume. Excluded volume, it is generally represented by B. This is the excluded volume. And what do you mean by excluded volume? Excluded volume is that volume of the total volume in which the other gas molecules cannot enter. This is the restricted volume. And just like, suppose this is these are the blades of a fan. Suppose its volume is 1 meter cube or 1 centimeter cube. Suppose it has volume of 1 centimeter cube. What will be the total volume of the blades? 1, 2, 3 and 4 centimeter cube. But if the fan is revolving, this volume, and this volume, it will also get covered up. When fan is stationary, you can touch here, you can touch here, here and here. But when the fan is revolving, you cannot touch here because this volume will be covered up. And obviously, this will get excluded. Likewise, if the molecules of the gas, they are stationary, then 8 by 3 pi r will be the actual volume. But when the molecules are moving, then not only the actual volume, but this much volume will get excluded. It means we are thinking that total volume of the gas molecule is negligible. If they are stationary, then the volume will be negligible. But here, they have covered the more space, more volume. So now they will not be considered as negligible. So what will be the volume of this excluded volume? 4 by 3 pi 2r cube. Because if this is the excluded volume, its radius is this, and this is 2r, and obviously 8 by 3 pi r cube into 4. If I replace it into 4, this side and 2 into 8, I have written in this way because I can just explain that this B, excluded volume B, it is equal to 4 times the actual volume. The actual volume of the two gas molecules, that was 8 by 3 pi r cube, and their excluded volume is 4 into 8 by 3 pi r cube. It means this volume is 4 times the actual volume. So no doubt, gas molecules are very much small in size. Their actual volume might be negligible, but when they are moving around each other, there is some excluded volume, and that excluded volume is not negligible because it is 4 times the actual volume. So, what is the volume fraction? In that equation, we have written just V. This is the total volume. But now, we will write V minus V. What is V? excluded volume. Excluded volume should be excluded from the total volume. And for obviously n number of molecules or n moles, there will be correction B minus n. So this is the main thing after volume correction, that when volume will be corrected, then we will not use V, we will use V minus NB. This is the volume correction. Clear? Now, number 2, there will be pressure correction. Pressure correction. Why pressure correction? We were talking about intermolecular forces, because pressure is nothing but a force. What is the definition of pressure? Pressure is force per unit area. So, if there is correction in intermolecular forces, obviously there will be reduction in pressure. So, let us consider a container in which gas is filled, and if we consider this gas molecule in the bulk, obviously it will be surrounded by same type of gas molecules, and it will get attracted by a similar type of gas molecules from all the directions, and there will be no net force acting on it. And when this gas molecule is about to strike on the wall of the container, obviously this side there will be gas molecules, this side there will be gas molecules attracting and balancing each other. But gas molecules in this direction, in this direction, in this direction, they are not balanced, because this type of these forces, this force can be balanced if this there will be molecule on this side. These three type of forces will attract this striking gas molecules inward. When a particular gas molecule is here, it is feeling no intermolecular forces. But when it is about to strike on the wall of the container, then it will get attracted by the bulk molecules. It means throughout life, in the bulk, gas molecules are feeling different type of forces. You can say larger forces. But when they are about to strike, they are attracted, and they cannot strike with greater forces. They cannot strike with greater forces. They have greater forces. They have greater forces. But when they are about to strike, they are not impacting with those great forces. So pressure is reported to be lesser than the exact pressure. It means in pressure correction we have to add something. In that equation we have used pressure P, but here we will add in new pressure depending upon these forces, and this pressure is directly proportional to number of molecules per unit volume, number of gas molecules per unit volume going to strike, and this is also directly proportional to number of gas molecules per unit volume attracting the particular molecule. There are two sets of gas molecules. One set is they are striking on the wall of the container, and other set is they are attracting those molecules. So this pressure is directly proportional to number of molecules per unit volume going to strike, number of molecules per unit volume attracting the striking molecules. So this E will be directly proportional to m square upon b square, m square upon b square, and if proportionality is removed, it will be equal to an square upon b square. An square upon b square, and here we will write an square upon b square. This is the pressure correction, and this was the old ideal gas equation, but according to Van der Waal, what will be the new equation? P plus an square upon b square, v minus nb is equal to nRT equation, and we have made obviously pressure correction due to intermolecular forces. We have made volume correction due to extruded volume because it was 4 times, and this is the overall equation, and it will be valid for all the gases because we have removed the faulty assumptions. So this is